All right. So that should do for that. And I ought to mute the participants so they don't annoy one another. All right. Okay. So the schedule, such as it is up there. And we're down to programming. Let me save this. All right. So that should be right here. Yeah, all right. Those folks are obviously very distracted by whatever they're doing in biology. So, all right. So if you people have ever done any programming, you'll probably know a lot of what we're talking about today. But the point of this is not to make a programmer out of you, which is a big job. And we have a whole CS department about that, but to make it so you can understand the most common security problems that come from these languages and how to fix them. This is a huge issue in this field. There is the current tradition, which is essentially universal, is that programming is called computer science for some strange reason, although it is not science at all. They don't make hypotheses and perform experiments and prove things. And then what they learn is programming, and they don't learn any security at all. They typically don't even have a chapter in the book. The authors don't know anything. The teachers say they don't know anything. I bring it up to them. They don't want to hear it. And they say, quite correctly, our program is all full with programming people have to learn, and they have no time to learn security, which is a separate, huge discipline. So maybe I gotta close this one too, right? All right. Anyway, so what happens is they hire a team of developers to write stuff. They make the same mistakes that people have been making for 20 years, and then they hire another team of people called security experts to patch it. So it sounds nuts, but it's job security for us. So that's the way it is. There's a very small group of people that are complaining about this and trying to teach security to coders, but they're mostly getting nowhere. I'm one of them. And Dan Kaminsky does not support this much. When he gives talks, he says there's no point at all trying to teach coders to think securely because they really have too much else on their mind and it's asking too much. What you ought to do is build security into the development environments like Visual Studio so it happens without them knowing or caring. And that is the only practical solution. And that could very well be right. And that is what Microsoft did. Now, Microsoft was the king of this. Until 2002, Microsoft officially ignored security. It was their official policy that it is a waste of time to make a product strong enough to withstand a malicious attack. The only thing that makes any sense is to make a product that works when an honest user is trying to get work done. That is all that really matters. There aren't very many hackers. There's nothing to worry about. You just need to get features rolling out that do real work for real people who are trying to do work and forget about those idiots that are making trouble. But by 2002, this technique didn't work anymore, and they switched to being secure by default. But they made all their developers stop and read a book called Writing Secure Code, which you can still get from Microsoft, and they had to rewrite their stuff with security in mind. And they wrote a bunch of C libraries that removed the most dangerous functions in C that were responsible for most of the problems in Windows, and they published it so other people can use it. So they did both approaches. They trained their security developers, and they improved the language by adding more libraries to make the language intrinsically safer, and it made them much more secure. We had an engineer from Netflix come give a talk here, and he gave a talk about how wonderful it is at Netflix. They are apparently very well known to have a very high quality team, very high quality stuff. And I said, you want any of our students? He said, no, I don't want your interns and I don't want your graduates. We don't hire anybody fresh out of college because nobody anywhere gives you any training program that teaches you to write secure code. There is no certificate, no degree anywhere that does it. So the only thing we won't even look at you until you have 5 years of real development experience. That is the only place people learn is in combat. And so that's the current state of the world. So here's how it is. This is how you become the security professional. This is the first step, of course. It gets much deeper than this, but this is how you become the security professional who will then audit the code written by the developers and send it back for rewrite and generally make everybody hate you. And that's the current situation. They write stuff that they think is fine. They give it to you. You complain about stuff they don't even know what you're talking about. And there's an internal conflict coming from that. And you may have noticed that security people tend to be hated by the world at large. It's just troublemakers. And, you know, you have to sort of get used to that. Remember, you've kind of gotten used to being the bad guy. Anyway, so we'll talk about programming. C is responsible for a very large portion of the security problems until about 6 years ago. C is a very dangerous language. And from a security point of view, it's probably not a good idea at all. The good thing about C is it runs really fast. The bad thing about C is it doesn't make any attempt to improve your thought process. It just does exactly what you told it to do, no matter how stupid it is. Get a 1 gallon bucket. Yes, sir. Put 10 gallons of stuff in it. Yes, sir. Jump off this cliff. Yes, sir. Pull out your pistol, shoot yourself in the head. Yes, sir. It has no argument, does whatever you tell it to do, when many other languages are smart enough to notice that this is abundantly stupid. So, all right, in general, computer programming is writing down exactly how you want to do something, step by step, and then coding it in a language, and each language has their particular rules about semicolons and parentheses and stuff. Nobody can do this perfectly. It's my students who are sort of sloppy readers and sloppy writers that don't really bother with punctuation and spelling find this excruciating. It's like playing chess for a living. And the main thing is every mistake you make will lead to some degree of trouble. So the fundamental concepts that make a programming language are branching, looping, and testing. There are other languages out there like HTML that are not programming languages. They make it possible to put out text and say, make this letter big and make that letter small and make this into a list and put an image here. But there is none of this stuff. You can't count from 1 to 10 or repeat things or have an if statement that makes a decision. It's not a programming language. It's a markup language. It's just a description of how things should look. So branching is where you somehow jump from one part of the program to another. In the very early languages like BASIC and Fortran, you would use goto. People rapidly discovered, I was one of them, that if you use goto, pretty soon you've made spaghetti code. You don't even know what's going on anymore, where it jumps here and it jumps here and it jumps back, and you don't even understand what comes before what. So looping is where you can do something over and over, some number of times, and testing is where you can check some condition, and if it's true, do one thing. If it's false, do a different thing. And if you have those 3 things, you can solve all the problems in the world that are, I think, NP complete or something. There's P is the hard problems and NP is the easy problems, and they might be the same and no one knows. But anyway, there's a whole class of problems that can be solved, and every programming language can do exactly the same thing. They can solve that same class of problems. So in the early days, like the 70s, we all thought that one language would win and all the rest would go extinct. And that didn't happen at all. There's hundreds of them. There's more every week. It's nuts. But it turns out that even though in principle they are all logically identical, in practice one is easier to use than another for a given task. So you typically know a lot of languages. But C is one of the earliest languages. It started it all, and it became enormously popular because C makes the most efficient code that is smallest. And when you compile it, you can sell 1 million people a copy of your C program like Microsoft Office, and it is very difficult for any of them to steal it or copy it or modify it. They're pretty much stuck with what you give them because you give them only the compiled version, and it's difficult, although not impossible, to read and understand the compiled version. So you make a program, you have source code that ends in C, and this is more or less human readable. And then you compile it, and you make it into object code, which is almost impossible for humans to read. Anyway, it's typical to put comments in your lines like this, /* and //. Most professional programmers have very strict rules about commenting. Companies require it. It turns out, as you would imagine, that if one programmer writes something and then 2 years later some other programmer tries to modify it, it's next to impossible. It's usually much faster to just throw it away and write it from zero than to understand what somebody else did, unless they are very logical and very rigorous about writing good documentation, and almost nobody does. So this is the thing that's going to lead to a whole variety of entertaining security problems. It turns out that all modern languages use this modular programming style where you make subroutines. This turns out to be enormously powerful. So if I want to print something, I don't just write some code that prints it, and then for every program that prints, write some code that prints it. I write one routine that prints something and put it in a library, and they all share the same code. Now, this is really efficient because we don't have to keep writing print routines over and over, but it has two security consequences. The first thing is if there's a mistake in the library, it affects a lot of code. And that has happened over and over and over. And the other thing is you have this complicated and dangerous process where you're in main executing code. So here we are in main, enter age, enter the age. First line, I define a variable called age. Next one, I want to print something. So I stop executing main and I transfer execution down into a subroutine called printf. I print something, and then at some point I'm done printing and I want to go back and pick up where I left off in main. Now this means I have to somehow store the condition of the main routine and someplace and save it, then do all the stuff that happens in print, and at the end I have to somehow recover all that stored information and come back. And this step, coming back up, turns out to be fraught with security risks. It is actually quite easy to confuse the program so it does the wrong thing when it's coming back, and you take over control of the machine. And this was about 80% of all Windows exploits used this technique until about 5 or 7 years ago when Microsoft finally was able to put in some really powerful defenses against it. So, but anyway, this is how program flow goes. You're in one routine, you call a subroutine, then you return. Then later on you call another subroutine and return. And this one might call another. You might be 7 or 10 or 15 layers deep in subroutine of subroutine as you go along. So then there's looping. And here's another bit of madness. When I started, there's a long extinct language called BASIC. And you would just write for I equals 1 to 10. Do stuff, next I. You never had any problem with that, so it went completely extinct and was replaced by one that no one can understand, which is this one. This is how C does it. For I equals 0 is the current condition, semicolon, then comes the testing condition, then comes the changing condition. So this is going to start with I equal to 0, continue as long as I is less than 11, and add 1 to I every time. So here's a fun question. How many times is it going to print that sentence? I will not hack in class. I got a vote of 10. Any other votes? You like 10? Okay, 10 is wrong. Any other guesses?
11.
11. Because it's going to print for 0, then it's going to add and it'll be 1, so it'll print again, then it's going to add again and go from 0 through 9, then it's going to add and be 10. 10 is still less than 11, so it's going to print for 10, and that's when it'll stop. It's going to count from 0 through 10, and there are 11 of those. This is responsible for a huge category of bugs called the off by 1 error, and there are many, many security disasters caused by this, because no matter how much you do it, nobody can look at that and tell easily, clearly how many times it's going to happen. And if you change the less than to a less than or equal, or you start at 1, it changes. And so what happens is even experienced programmers are wrong about how many it's going to do frequently. So something that should have happened 3 times happens 4 times or 2 times, and that often opens a hole you can drive a truck through. So the algorithm is just the logical steps. Just do this, then do that, then check this, and if this happened, go do this other thing. Bugs are mistakes you make. Everybody makes mistakes. It is a good idea to write things down in pseudocode or a flow chart first, where before you bother worrying about the semicolons and parentheses, you just decide what is each part of it going to do. All right, and various things are popping up, but I think I'll just minimize them if I can get my mouse cursor back. All right, I don't know what it's trying to tell me. If anybody's trying to reach me from the remote viewers, the chat is probably the best thing. All right, anyway, so here's what pseudocode might look like. You're going to go shopping. So you make a function called purchase ingredients, and that's going to call further functions like get car, drive to store, purchase these specific items. Then you're done purchasing ingredients. Then you've got to drive home, heat up the oven, cook things, and all these things. That's the pseudocode where. And this turns out to be enormously efficient because now you can have a team of programmers. You can have one person that say, your job is to write a routine that will start the car. That's all it does is start the car and get it working right. And everybody else will just use that one. And by breaking a job up into small jobs, it turns out to be much easier to make maintainable code, where most of it still works and have the new feature. We'll just have to change these 2 routines, but nothing else. Yeah.
That's what they would do with like Microsoft Office things as a huge.
Yes. And you could, in the early days, you'd just have a huge blob of code, 10,000 lines, and when you wanted to add a new feature, you'd have to go change all of it. Now you break it up into modular logical chunks. So if a new printer comes out, you just have to write a new bit to the print routine, but you don't have to touch anything else. It makes it much more logical, easier to maintain. On the other side of that is the business model of Microsoft. The Microsoft Windows operating system is like the Frankenstein monster. What they typically do is another company reads Microsoft's documentation, which is far from perfect, or maybe they don't even read it. They make something like an antivirus or a file handler or a game or a security product or a useful office product, and they get more and more money until they're famous, and then Microsoft buys their company and patches it into Windows. So you end up with something like the Frankenstein monster where a clock comes here and a clock comes here, and so weird things happen, like they made the same security mistake 3 times in a row, like 4 years apart, maybe 10 years ago. They kept on encrypting stuff with no nonce because they bought a company that did that, and then they had to patch it. Then they bought another company that made the same mistake without noticing, patched it in, and it was in there again. This tends to happen, and it's all to make money. Bill Gates was never shy about this. He's in this game to make money. He's trying to make software that makes money. He's trying to make it easy for developers to make money. He just wants to get the product out fast and good enough to make money. He's not trying to be perfect or logical or anything. That's his goal. It's capitalism. And the most efficient way, if somebody writes something great, is swallow their company and patch it in. Now we've got these great features and on we go. All right, so you have to document your stuff. As I've said, most programmers, however, find this time-consuming and tedious, and it is one of the painful jobs in the industry to somehow make the programmers actually document their stuff in a way that someone else can read it. So there's lots of bugs. I've seen estimates up to 2 or 3% of all the bugs. I don't think anything I write can withstand 2 or 3% and still work at all. But anyway, there's certainly bugs. Windows 2000 had 60,000 bugs in its 50 million lines. The source code leaked. So that's 1 per 1,000 lines. Linux claims to have even 6 times fewer bugs. One thing about Linux, of course, is you can see the source code, so you can run some kind of scanner and try to find the bugs. Although, of course, there is nothing you can buy or build that will find all the bugs. That's why they're there. The ones that can be found with a scanner, people pretty much find them and remove them. There are other ones that are just very difficult to figure out because nobody knows exactly what you intended to do. There's no perfect scientific way to see if the code is doing what it's supposed to do. So C was developed in Bell Labs in '72. It was very powerful. The point of C was to write Unix. And the point of Unix was to unify operating systems. I was in the game way back here, and at this time, you would buy something like an IBM mainframe, and it would come with about 10 telephone books full of IBM mainframe programming language, and you had to learn that for the IBM. And if you bought an Amdahl, it was all different. If you bought a VAX, it was all different. So you had to focus on one brand, and one brand could not talk to the other brand. So you could never have the internet. So at Bell Labs, they finally figured out this is for the birds. We want to have one language called Unix. And we will use Unix to write a C compiler for every machine, and then they will all speak the same language for programming and for communications, and then we can have the internet, where an Amdahl speaking Unix can talk to a VAX speaking Unix, and IBM speaking Unix using these unified protocols. So you had to have a language that would go everywhere. C was enormously useful. Yeah.
Isn't Apple based in Unix?
Yes, Apple is based on Darwin Unix, which is based on BSD. So that's why Apple advertises their product as the most advanced operating system in the world, and that is not a stupid thing to say. BSD Unix is one of the main Unixes right from the start. So it is the oldest and most perfected language. And that's why things like the London Stock Exchange run on Unix. It is handling a lot of data. It has to be really fast and really reliable and just stay up and never crash. So they used Unix for years until Microsoft managed to persuade them to switch to Windows Server. I think it was Server 2008. And they trumpeted they were going to do it for like a year in advance. Say, our product is finally so wonderful, they're going to use it to run the stock exchange. And they switched to it, and it crashed completely. And the London Stock Exchange went down for 3 days, which was a historical disaster. And they went back to Unix. I mean, Unix is what you use when you really, really have to stay up. And Windows is what you get when you want it to be easy to train your workers and easy to use. But nobody ever pretends that it's really going to stay up with the kind of reliability you get from Unix. It's really much younger, much less perfect language. Now, what's really going on in your machine is machine language. This is put in there by the designer or the processor, and you cannot change it. So the fundamental machine language is just a way to take a pattern of bytes and interpret it as a language, like add register A to register B and put the result in register A. That's a common command. And they just have a pattern of voltages that come in the wire that mean that, and then it will do that calculation. That's essentially impossible for humans to read, so they made this thing called assembly language, which attempts to make machine language somewhat readable. So you have things like push 70H. That'll take the hexadecimal value 70 and put it in a memory region called the stack. Then you push something called offset up in the stack, then you call a subroutine at this location, then you do an exclusive OR and a push and a move, and these little tiny instructions that flip just a few bits at a time add up to everything your computer does. Writing assembly language is a valuable skill, especially for people who want to develop exploits, but almost nobody that actually wants to get anything done writes in this language. It is extremely painful and difficult. You would prefer to use a language like C or Visual Basic or Java or Python to write stuff, and then let the computer translate it into this stuff. So C, you need a compiler to use C. If you write that source code, it will not run. You have to first translate it into machine code to run it, and that's what the compiler does. Ubuntu Linux does not come with a compiler. You have to install this thing called Build Essential to have it, because most people that are using Ubuntu Linux are like people using Windows. They are not developers. They don't know any languages. They don't care. They want something like a browser and a word processor and the ability to play games. And so there's no point giving them a compiler because they're not going to use it. You put it on only if you're a developer and you're going to do it. So you then compile things this way with GCC for GNU C compiler. Give it the name of your source code and then the name of your output code, which is typically the name of the code without any extension. That's typically the executable code. So every program starts with main. It does not have to have this include statement, but it almost always does, because you usually want to use some of those libraries. You don't have to write everything. And then you have a main with open and closed parentheses, and then you have a curly brace and a closing curly brace, and in there is the main routine. And you have to have a main routine because that's where it starts. If you have any other routines, they have to be called by main. All right. Comments, you can put them in with this /* and / if you want to. There's other ways. The include statement includes a library, and you typically want to use a bunch of libraries in your C code so you don't have to bother writing code that prints things out and reads a file from the disk and so on. Yeah?
When we include a library, does each library increase the risk of security flaw?
That's a very good question. And for the remote users, he's asking whether a library increases the risk of a security flaw, and like everything else, it could go either way. For example, there have been some bad libraries in Android and in iPhone. In iPhone, there was a bad library included that broke verification of HTTPS certificates. So a whole bunch of iPhone apps had a flaw for a long time. So, I mean, it's like asking, we had a question like that at this college. We had our own email server, and it kept on crashing and getting full and failing. And so I said, let's just go to Gmail. And the question is, would that be better than running our own server or not? And then the question is, are your server administrators better than the server administrators at Google? They might be. So the question here is the guy that wrote the library smarter than you or not? If they're smarter than you, it's better to use the library. If you're smarter, it's better to write your own. That's the answer. It's not a very nice answer, but for most businesses that just want to get the job done, it saves a lot of money to use the library. So you don't pay your staff to redo some work that somebody else already did. So that's usually what you do, is use libraries as long as they're well established. The problem is sometimes there are disasters like Heartbleed and like the Ubuntu random number generator. The main branch of Debian, which is the main branch used in America of Linux, Ubuntu comes from Debian, Corley comes from Debian, many other things do. The main branch of Debian didn't compile with an update about 5 or 6 years ago, and somebody commented out one line that was failing to compile, and that was the line that seeded the random number generator. So for 2 years, all the random numbers were no longer random. They were all just pulling from the same starting point, the same series of numbers. So all the security certificates, HTTPS certificates made for 2 years on all of the Ubuntu family of Linux were trivially crackable because the random numbers weren't random. And that's what happens. Over at Heartbleed was the same. Somebody made one change in the code for OpenSSL, which is a library used by almost everybody in the world, and it was never caught. And so again, for 2 years, every HTTPS server on the world was just leaking everything, and nobody noticed. At least we hope nobody noticed. It's possible that somebody noticed and stole all the data for 2 years, and nobody will ever know that didn't happen, because you could steal all the data and there'd be no record kept. Now that's the problem. These libraries are good and bad. So then there's functions. You make a function here, it does one thing. You start with a name, in parentheses, then you have curly braces. So the main is a function. The operating system itself is running, doing things like showing the desktop and the terminal, and then you double-click an icon to start your program, or you type the name of the command prompt, a terminal, and then it jumps into the program starting at main. Main itself is a subroutine, one step down from the operating system. And when it calls things like printf, it's now 2 steps away from the operating system. And when it reaches the end, it has to come back and back to get back to the operating system. All right. The functions can call other functions. So you go down here, and on you go. This \n is a special character that gives you a carriage return. There's a variety of them. An enormous number of security flaws come from special characters being mishandles. One environment might interpret the /n as terminating something, but the other environment doesn't. Especially null bytes lead to a lot of trouble. And we'll talk about some more of those as we go on with the class. In C, you have to define all your variables. This is because it's very close to machine language, and it's responsible for the entire category of problems called buffer overflows. So if I'm going to have an age that's an integer, I have to tell it it's an integer. There are different kinds of integer, and by being integer, it's a short integer. So this means I can't put characters in it. I can't put fractions in it. I can only put in integers or numbers, and I can only put them into a certain maximum. So if I keep adding and adding and adding to that, after a while it will roll over like your car's odometer and become negative. And there's a whole variety of integer overflows and integer underflow variables that come from that. There's a, I forget which product it is, but there's a product that inside C where you had some character length, like you can only put in 100 characters or it'll stop you. It said if the number of characters is less than 100, it's okay. If it's greater than 100, it's not okay. So all you had to do was put in like 2 million characters, which would roll around and be interpreted as -1,000, and now it would think that was okay. So this kind of stuff keeps on happening. You have integer variables, you have floating point variables for numbers with decimal points, you have double precision, but you don't have any infinite precision. Everything has a limit. And you have characters for individual characters and strings for a null terminated string, which leads to no end of problems because you have to leave 1 extra byte of storage available for the null character. And it is very easy in C to overwrite or lose the null character, and then your string has grown for all the random bytes that happen to be in memory beyond it, and turns out to be much bigger than you think it is. And it turns out to address areas of memory that you were not supposed to be able to address. And that gives you dangling pointer type vulnerabilities, where there is a variable I can read or write that points to something I was not supposed to be able to access. You can often take over the machine through them. So you can add things, plus increment something by 1. You can do multiplication, modular arithmetic, division, by subtraction, all division, all the stuff you want to do, of course, is available. And you have logical operators like I less than 11, I less than or equal to 11, I equals 11, and so on, for every possible comparison of things, which results in either true or false and can be used in an if statement. So I got a few cahoots about this stuff. So let me bring that up. So that's the basics of how programming works normally, and now we're going to start messing it up, which is, of course, why we're all here. We're here to break things in this class. We're not productive, we're destructive. So it's a lot more fun to be a breaker than a builder, especially at the beginning. Being a defender is extremely difficult and a very advanced skill, and we're only gradually moving into that. Anyway, because the defender has to think of everything. The attacker just has to find one mistake that somebody made. It's intrinsically easier. All right, so I'll wait a while while these cahoots come in. I'm not going to try to call the roll. Since so many people attend online, I think I'm just going to say whoever turns in the homework counts as being here. That's probably the more accurate way to measure it. Jump, call, pop. There you go. So it's 10:18. All right. Okay, I'll wait another 10 seconds to see if we're going to get any more. All right, Looks like we're losing them rather than gaining them, so we might as well go. All right, 5 questions. All right, which function is not required? All right, that's inheritance. Inheritance is a property of object-oriented languages, and it's cool, but you don't really need it. It's a convenience. All that you really need is branching, looping, and testing. All right. 2% of code consists of what? All right, bugs. That's what they say. Estimates vary. Which language came from Bell Labs? All right, that's C. Good. Which one is built into the processor? All right, that's machine language. Assembly language is number 2, but assembly language is just an attempt to make machine language readable, and there are, in fact, 2 different common versions of assembly language, but there's only one machine language, whatever is built into the processor. All right, so how many A characters will that thing print? All right, it's 9, not a very popular answer at all. This is, and this, yeah, it starts at 1. So it goes from 1, 2, 3, 4, 5, 6, 7, 8, 9. It only continues as long as you're less than 10. So it only goes from 1 to 9. All right. Anyway, all right. All right. So the winners, William and Cam and Blunder. So I know Cam and Blunder. William will have to tell me who he is. I'm going to stop the share and restart it. Just, well, you know, it's getting close enough to the hour. Maybe we'll take a 10-minute break and pick up at 5 minutes to 7. That's probably the logical thing to do. And then we'll do the next bit of this. All right. So I'll stop this for about 10 minutes. I'll be back.